Please complain if it's not, but at least I can hear myself better at the moment. And so, my name is Valeria de Paiva, as you can see in the slide, and this session, which will consist of 3 lectures, is going to be quite a bit different from Brigitte's introduction letter in the morning. We're going to do some overviews here, and we're going to do it in a very story-like fashion. And while Brigitte and Anya and lots of the other lectures are going to be going over very specific systems and trying to get you to calculate stuff, I'm going to be more of a storyteller. And that's for 2 reasons. The first reason is that I think we are in a moment in terms of computing in general where you need to think hard about where we're going. And one of the ways to think about where we're going is actually thinking a little bit about how we came to where we are. And that's kind of reason enough to be thinking about history. But the other reason is very much because I think people in general like stories. So this series of lectures has lots of stories, kind of, and not very much deep discussion of specificities. But you're perfectly welcome to kind of grab me after the lecture and try to talk to me about specific items and specific things that you want to know more about. And so, to kind of carry on this theme of things that are very superficial, but trying to cover an awful lot of ground, some of this stuff that I'm talking about today was also a talk in the Strange Loop 2023, and Jim kind of posted some of old talks that I've given about this, so you can store up questions for me if you want to. Okay, so let's see how it goes. Oh, before anything else, thanks to the organizers for the invitation to be here today. So Zina, Alexandra, and Sylvia, thanks a lot. And as I'm saying, this is a little bit of a PR, a propaganda sort of stuff, because I kind of helped to co-found something called the Topos Institute, which is situated in Berkeley. And we have a very different approach to some of the themes that are part of the school and have been part of the school for the last 20 years. So we actually think that we could try to use our kinds of technology to improve the life and improve society. So we think that we hope to shape technology for public benefit by advancing sciences of connection and integration. And what we do want is a world where the systems that surround us benefit all of us. So it's a not-for-profit, but startup in Silicon Valley. And I thought I should start by telling you a little bit about my personal journey into this stuff, because as you will recognize kind of quickly, I'm not a traditional lecturer. I come from 26 years in Silicon Valley, first in Xerox PARC, then in startup trying to dethrone Google. It was called Cool and it was a big disaster. And then some more traditional places like Reading and Nuance and kind of especially Samsung. But this is all kind of sort of computing that is kind of different from what is happening now, because this was mostly AI, traditional AI, so logic-based AI. And the reason I'm here is because in 2020, when Samsung kind of decided to close their knowledge representation and logic-based user interfaces lab, and so all of us were laid off, I decided that I wanted to go back to some of the stuff that I was doing before, and that's what my background is in. And this is part of the fun of listening to this series of lectures, which is that you should try to guess who the people are. In this case, I'm going to, first one, I'm going to be nice to you and tell you who the guys are here. So the first one over there is Martin Hyland, who was my supervisor in Cambridge. The second one, very few people know who that is, but it's Robin Ganti, who was the one and only student of the guy over there, which I hope you all recognize as Alan Turing. So these are my kind of, Brigitte showed us how she connected to Alonso Church. So I kind of connect myself, I'm a great-granddaughter of Alan Turing using these three pictures over there. But my work has been based mostly on the work of Kurt Gödel, who you might not recognize because that's a younger version of Gödel. And that's why I think, there's an old joke that mathematicians, when they get old, they start being historians of mathematics. They prefer to think more about how things come to be. And, there is some truth to this old joke. So my outline for the three lectures that I'm giving is that I'm going to today talk about math, logic, and computation. Tomorrow I'm going to try to talk about linear and modal logics. And on the third lecture, I'm going to try to talk to you about explicit substitutions. As you may have noticed, all these things have been touched upon in Brigitte's lecture, and lots of them are going to be touched upon in all the lectures of this school, and have been talked over and over in previous issues of the school. But I wanted to show you my own view on these things. So, my version starts from mathematics, pure mathematics. And one of the things that I think very few people realize, everyone knows that relativity changed the way people think of physics, quantum physics changed the way even relativity is considered. Everyone knows that Darwin kind of reinvented the way we think about biology and stuff like that, but very few people think about what has happened in mathematics in the last century or so. 125 years or so. And there's a nice paper in the notices of the EMS by someone that I don't agree with mostly, Frank Quinn, but on this case, I think he's on the money. There was a revolution in mathematics, and it happened in the beginning of the 20th century, around the 1920, 1930, and it still matters today. It matters because it influences how we think about computing, and because it's a very implicit sort of revolution. So you have to look hard to see how things changed and are still changing. So one of the main things that happens, it's easy to see this kind of sort of revolution, thinking about algebra and proofs. Because, even today, if you say to someone that you're a mathematician, lots of times people are going to say to you, what? Mathematician? What do mathematicians do? Hasn't mathematics been all invented 2,000 years ago? Right? There's this feeling, the settled feeling that, that everything has been done in large parts of society. Of course, not here. I don't think anyone here would have this very naive idea, but in lots of places that's still the case, that people don't know what mathematics is about. And my contention is that mathematics is not about numbers, but about structures, connections, and proofs. And the way mathematics changed in the last 25 years of the 19th century and first 45 years of the 20th century was exactly this change into stop thinking about numbers that we calculate with only and start thinking about the structures behind those numbers that we calculate with. And one of the luminaries of this revolution really was Bourbaki. And Bourbaki, everyone here knows about Bourbaki, right? It's a joke, right? I mean, that's the problem. It's a big bad joke in some ways, because we still go to Amazon, and no one tells you that there is no person called Nicholas Bourbaki. He was just a pseudonym of a collection of mathematicians, French mathematicians, who exactly wanted to rewrite mathematics in the style that I'm talking about, the style that pays attention to proofs and structures. This sort of revolution is not completed. So it's to my mind, it's an invisible revolution, and there were no cataclysms, so there was no big things like quantum mechanics and people thinking that physics had disappeared in a black hole or anything like that. Euclid mathematics still taught in high school nowadays, but as I was saying, people don't understand what is research in mathematics and what is it good for. And we kind of need people to know about this stuff, because we need people to know that computing and mathematics are deeply intertwined. And I think that's one of the main themes that the whole school has been about. So there's still kind of, according to Quinn at least, there's still lots of shock waves going on in the world of mathematics, and some of the questions that people pose are kind of meant to think about that. So there's this business of whether math is invented or discovered. There's this business of what foundations, if they're essential or silliness. There's this huge discussion about whether there is a unique, correct framework, or there should be pluralistic foundations for mathematics. And I think, I'm pretty sure that everyone here is aware that we are kind of in a new kind of revolution at the moment. Even the New York Times is talking about mathematics and computing, right? They are talking about AI is coming from mathematics, and that is that's one of the reasons why I think people in this summer school should be thinking about where our community is going and how we're going to get there in good shape. So all these sorts of questions about revolutions and things like that, I think my personal tool or weapon, or whatever you want to call it, is category theory. So we will see lots of type theory here. You already seen some, even if it was not calling itself type theory in the first lecture from Brigitte. It was talking about logic mostly, and judgments that kind of, you can think of logic in terms of judgments. We will see lots more of type theories of different shapes. used for different things like security, like protocols, like verification of all sorts and shapes. But yeah, kind of the thing that I want to sell to you is this idea that category theory is a good weapon, a good tool, one that you should have at your disposal and kind of whip out whenever you need it. So, I mean, but you know, like everything else that is taught in the summer school, teaching category theory takes a while. You know, people try to compress all of the courses on category theory in 5 days, and there will be a course taught by Paige North about that and stuff like that. So, you know, it is hard to compress a one semester course into 5 hours or kind of whatever, a little bit more than 5 hours. So it kind of helps to have this sort of overview of why people like me think that that's a useful thing for you to spend some of your time thinking about. And I mean, I think it's important to remember that the same way as I was saying that mathematics is about structures and about proofs, kind of category theory in particular is about structures, yes, but mostly about how structures relate to each other. And the examples, the trivial examples, are the ones that maybe you're not totally familiar with. So let me check again. Has everyone have a degree in computer science here? Who doesn't have a degree in computer science? Well, there's quite a bit. What are your degrees on? Kind of engineering or mathematics or physics? Can I have physics? 1, 2. Can I have engineering? Different kinds of engineering? 1, 2. What else, guys? Math. Cool. Math. 1, 2, 3. Excellent. Very good. You see, can I ask another question on this one? How many people are from the US and how many people are not from the US? Hands up who's not from the US. Yeah, that's what I thought. Yeah, I mean, that's part of the reason for this talk being the way it is the fact that there's a huge cultural difference between computer science and theoretical computer science as it happens in Europe and other parts of the world, and what happens in the US, where things are much more geared to now, and kind of in 3 months, one, you know, which product can you code in the next 3 months? In other parts of the world, people tend to think a little bit in longer terms, and hence, you know, they will think that it's okay for you guys to separate some of your time and learn a bit about category theory. Here is a bit harder. Okay, let's carry on. Oops, too many. So now we want to talk a little bit about logic, and you've heard lots about logic already this morning, but I want to talk again about history of logic. And this is a very bad slide, I apologize, but it shows one of the things that I wanted to show you, which is this business that actually, if one thinks about it the right way, Curry-Howard correspondence starts to be conceived in 1847, because that's the year that Boole actually published his book on Boolean algebras. And if you think the way I think, which is that Curry-Howard is not just about relating logic and type theory, and thinking of type theory as being computation, but it actually has a third leg, which is mathematics and category theory, then, you know, you should start from 1847. Even if you don't agree with me on the kind of essential role of category theory, you know, you still have to kind of think about Curry-Howard coming from 1920, because that's when Schoenfinkel produced his combinators. I mean, actually, he actually presented them in Göttingen in 1920, but published in 24. And if you haven't seen it, you should go and check Wolfram's blog post about Schonfinkel, because it is a work of art, the blog post. He's explaining how, with all his money and all his mathematical kind of people to help him and stuff, how he actually just managed to reproduce some of the stuff that Schonfinkel had done totally by himself in 1920. I mean, hats off to Wolfram. He did a good job with the explanation and showing how he actually proves that the combinators that Schonfinkel produced. One of them you saw this morning in Brigitte's lecture, the K combinator. She did not show S yet, but will be coming soon, I think. So, it's over there, kind of in the middle. And I'm not actually talking about the bits that are interesting to most of you, which are kind of much later than 1945, but I kind of stopped in 1945 because of, I kind of wanted to at least talk about realizability. I'm using that as a way of gauging, of measuring some of the evolution of logical techniques. Right. So now we got to computation, but mathematical computation. But you guys are my guys, so that's okay. We like it. And as I was saying, you can think about the Curry-Howard as starting 1847, 1920 with Schonfinkel. Then the people that are kind of really considered Curry himself and Howard, 1969. And, and you're going to have 3 different series of lectures on the Curry-Howard, kind of. And it's not clear that you kind of come out knowing very much about it, because there is an awful lot of... what I wanted to say is that there is, when you change the way people think about things, it takes a lot to realize that something has changed. And I think that's the fact that we're talking about this invisibility of the revolution in mathematics. There's also this invisibility of this relation between mathematics and computation that is that can be labeled with Curry-Howard correspondences. But it doesn't have to. It's just one of the things that we could label it with. So, now start the business of the quiz. You guys can start discovering who the people are on the pictures, right? But I kind of have George, not Curry, as the representative for the Lambda-Calculus. We'll talk that because he created it. Then we have the logician Dag Pravits, who thank goodness is still with us and active. And in 1965, he actually made sure that all the beautiful systems that Jensen created and that Brigitte was explaining to you this morning, that they kind of worked the way they were supposed to work, meaning that he could prove normalization for classical logic as Jensen wanted initially. And we'll talk a little bit more about it in a minute. And, my side of the story, that's Bill Levere, who recently left us. And he was the first one to actually connect in several ways these 3 bits. And this triangle is going to show up several times in this lecture with different people but in different logics and different Lambda-Calculi, and that's why the lecture series is called Logics and Lambda-Calculi. But yes, kind of because these things are not so old, it's kind of hard to know exactly not only who do you credit with things, but also what exactly is the concept that has been crystallized in each one of these the things that I'm going to be describing. Okay, so what is it? What is the Curry-Howard? It's a fundamental result connecting logics, programming language, if you think of the Lambda-Calculi as a programming language, as we do, and categories. And lots of people don't think of adding the categories there, but some of us do. And each of the arrows that I was showing in the picture before connects two of these things, and the connectors need to be done very carefully. They don't work if you're not careful about how you're setting things up. And it's very easy to destroy the connection by, like for instance, even normalization for classical logic fails if you're not kind of careful with your discharge function, which is something that people like me who are glib and superficial tend to not talk about. But there is a discharge function that you have to be careful that it satisfies a collection of properties, and that's why you need to have serious courses like the other ones in this summer school. So the original Curry-Howard does type logic and type theory, and the system that Brigitte is presenting is the paradigmatic one, is the canonical one, intuitionistic propositional logic, and category theory is a late addition. And as I say, you can learn much more about it in Kent North lectures. And also, oh boy, I see that we're going to have a problem. This was working fine, and it's working fine on the slides that you have, so I'll have to remember what was in the last lines of all my slides, but you have the real version, which I think has everything, hopefully. If not, I'll send another one. So as I say, I wanted to go a little bit about history, so I wanted to go a little bit about how the Curry-Howard comes about. And I think, I hope lots of you have heard about some of this story. And the start of the story is that mathematics was in a turmoil because of the paradoxes of set theory at the beginning of the century. In 1906, Russell came up with this idea that a naive notion of set led into paradoxes, in particular the paradox about the set of the sets that do not belong to themselves, and kind of was very mean to Paul Frege, who kind of thought he had sorted it all out and discovered that there was this big hole on this stuff. And Hilbert, who is another one of these unsung heroes of the story, came up with this idea that, think about it. Brigitte told you this morning about the idea of thinking about proofs as objects that we calculate with. But this idea that a proof is a mathematical object, it takes some thinking to get there, right? Because you think of it as a metalogical object. You say, okay, I'm proving that there are an infinite number of primes or something like that. I'm not you write the sentences in English, in Portuguese like me, or in French, or whatever. And that thing is a description of something that some reasoning. So to kind of come up with this extra step, like Hilbert did, to say, oh, tell you what, proofs are objects, and they can be studied by mathematical means, and we actually should prove theorems about them. It was important, and to my mind, very surprising. So Hilbert had this program to provide secure foundations for all mathematics, and his program was kind of based on the idea of formalization. And he kind of wanted to base, because he wanted to base all of it in the notion of finitistic methods. So he wanted to show that things like the Russell's paradox was not a problem that you could, if you thought about it carefully enough and kind of stratified your universe, you would never have a problem like something that looked like a contradiction, as Russell's paradox looks like, coming up on your mathematics. And so his main goal was to prove consistency of arithmetic. And he thought from that we would get the whole of mathematics sorted out, guaranteed. So how he decided to go about it, he had this wish list. He wanted to show that no contradiction can be obtained in the formalism that he was designing for mathematics. He wanted to show that all true math statements can be proven, so there is no ignoramus, or whatever in Latin. And he wanted to show that, okay, we need to deal with infinities. Infinities are important. And maybe we need ideal objects to deal with that, but things are going to be conservative. Any result about real objects can be proved, that is proved using ideal objects, can be reduced, can be proved again without the ideal objects. And he also wanted decidability, right? An algorithm for deciding the truth or falsity of any math statement. It was a tall order, he didn't get it. It just didn't work, right? Because Gödel came along and said, nope, incompleteness. There's no way you can have all of your wish list. Yeah. Sorry, thank you. What's up?
What did he mean by real objects?
I'm sorry, you have to shout because...
What did he mean by real objects?
Well, he thought that things like limits of sequences, for instance, kind of, they are ideal because you don't have a way of knowing, you don't have a finitistic method to get to them. And so all this, and he said, oh, there will be lots of other things like that, right? Kind of, you can go higher up very quickly, right? You think about sequences of natural numbers, then you think about functions, and then you think of functions of several variables. All of this stuff is idealized. It's kind of, you kind of invented for yourself a notion of infinity, and you carry on with that notion, and if you're lucky, everything will work out. So his idea was that whenever you kind of had a consistent thing like that, you could reduce it to finitistic things that then you would prove that the finitistic things inductively generated the ideal ones. I mean, this is all, as I say, glib and superficial, but I will give you the specific things to read if you want to. And that's the other thing, guys, I'm a little bit deaf, so if you want to ask questions, yes, I'll come to you in here, okay? Right, so Hilbert's program proved impossible if interpreted in the most direct way, which is